All right, today we're going to dive into one of the absolute weirdest, most fundamental ideas in all of physics. I'm talking about a concept that completely flipped our understanding of reality on its head. It all boils down to a question that, at first glance, it doesn't seem to make any sense. So what is light, really? For hundreds of years, this question had scientists basically picking teams. Is it a continuous flowing wave, like ripples on a pond? Or is it a stream of tiny little bullets? The answer, it turns out, is a completely mind-bending yes. You see, in the world of classical physics, these two things are complete opposites. A wave, it's spread out, right? It can interfere with other waves, creating these cool patterns. But a particle, that's a tiny, specific dot. It's here, not everywhere. You can point to it. There's no in-between. Or so we thought. So for a really, really long time, this whole debate seemed to be over, and it looked like Team Wave had it in the bag. The evidence just kept stacking up in their favor. The knockout punch really was the famous double-slit experiment. So imagine you shine a beam of light through two tiny little slits. Now, you'd expect to see just two bright lines on the wall behind, right? But that's not what happens. Instead, you get this incredible pattern of many bright and dark stripes. That's a classic sign of wave behavior. It's called an interference pattern. The only way to explain it is that the light waves passing through each slit are interfering with each other, kind of like when two sets of ripples in a pond cross paths. The case seemed closed. Light had to be a wave. But hold on. Just when everyone was getting comfortable, something new popped up. As we rolled into the 20th century, there was this one pesky experiment that just didn't fit. The beautiful, elegant wave theory had no answer for it. And it wasn't just a small problem. It was like a crack appearing in the very foundation of physics. That crack had a name: the photoelectro effect. On the surface, it sounds simple, but hiding inside was a secret that would change everything we thought we knew about light. So here's the puzzle. The experiment is easy enough. You just shine some light on a piece of metal, and what happens is electrons get knocked loose. But here's the weird part. If you used a low-frequency red light, nothing happened. You could make it super, super bright and still nothing. But then you take even a really dim beam of high-frequency violet light and boom, electrons start flying off instantly. Now, according to the wave theory, a brighter light is a more powerful wave with more energy. So a bright red light should have worked eventually, but it didn't. It was completely baffling. It just made no sense at all. And then along comes this young guy in 1905, Albert Einstein, with this totally wild idea. He basically said, what if we're thinking about this all wrong? What if the wave theory isn't the whole story? He proposed that light isn't some continuous flowing wave. Instead, it's actually a stream of tiny, individual packets of energy. He called these little energy packets quanta. Today, we call them photons. So think of it this way. A photon is a single, discrete particle of light. The big idea here is that light comes in chunks, not a smooth flow. And this was the key that unlocked the entire mystery. See, a photon's energy doesn't depend on how bright the light is. It depends entirely on its frequency, which is basically its color. So a single violet photon with its high frequency has just enough punch to knock an electron out. A red photon with its low frequency, not enough juice. And it doesn't matter if you send a billion of them. If one can't do the job, none of them can. It's an all-or-nothing deal. And just like that, the puzzle was solved. Light was behaving like a particle. Okay, so light, which for ages we were sure was a wave, can also act like a particle. That's a huge deal. And it got another brilliant mind thinking, if a wave can be a particle, could it work the other way around? So in 1924, this physicist, Louis de Broglie, asks this just absolutely audacious question. He says, okay, if light waves can pretend to be particles, what if particles, like, say, an electron, can pretend to be waves? What he loved was the symmetry of it all. It was just so elegant. It hinted at this really deep, fundamental connection in the universe. I mean, if nature gives light this amazing two-faced character, why would it stop there? Why wouldn't matter get to play the same game? And he didn't just stop there. He came up with an equation for it. He basically predicted that any moving object, anything that has momentum, also has a wavelength. Yeah, that means you, me, a baseball flying through the air, we all have a wavelength. Now, for big stuff like us, that wavelength is so ridiculously tiny we could never ever notice it. But for something as small as an electron, Well, maybe, just maybe, you could actually detect it. I mean, what a hypothesis, right? But in science, a cool idea is just that, an idea. You need proof. Someone had to design an experiment to see if these matter waves were actually real. And that proof came thanks to the Davison-Germer experiment. And the setup was beautifully simple. All they did was shoot a beam of electrons, those things everyone knew were just tiny particles, at a nickel crystal. So let's stop and think, what should happen? If electrons are just little tiny billiard balls, they should just bounce off the atoms in the crystal and scatter all over the place, right? That's what all of classical physics would predict. But that is not what they saw, not even close. What they saw was absolutely shocking. The electrons came off in this very specific, orderly pattern. It was a diffraction pattern, the exact same pattern you get when waves bend around an obstacle. There was no other explanation. It was undeniable proof. Electrons, the textbook example of particle, were acting like waves. De Broglie? He was right. Look, these two discoveries, light acting like a particle and particles acting like a wave, this wasn't just some quirky little footnote for a science textbook. This completely shattered classical physics. It wasn't like they just found a new rule. It was like realizing the entire rule book they'd been playing by was for a completely different game. So what's the big takeaway here? The main thing to get is this. At the most fundamental level of reality, things aren't just one thing or the other. They're both. Light is a wave and a particle. An electron is a particle and a wave. This idea, wave-particle duality, is the absolute bedrock of quantum mechanics. It's the set of rules that governs the unbelievably weird world of atoms and subatomic particles. And don't think this is just some abstract theory for a chalkboard. No way. Understanding that electrons have a wave nature is the reason we can build electron microscopes powerful enough to see individual atoms. It's the core principle behind the semiconductors that run your computer, your smartphone, everything. This bizarre quantum idea is quite literally the engine of our modern world. So, this dual nature of everything is a pretty powerful reminder that the universe really doesn't care about our common sense. It doesn't have to follow the rules we expect it to. It's way stranger, way more interconnected, and honestly, way more fascinating than we ever could have dreamed. Which kind of leaves us with one last question to chew on, doesn't it? What other obvious rules about reality are just sitting there, waiting for the right experiment to come along and shatter them completely?